Have it? The balanced chemical equation? It's a little bit tricky, but we have copper 2 sulfate reacting with sodium hydroxide. What forms when copper 2 sulfate reacts with sodium hydroxide? This is a double replacement. AB plus CD yields. Yeah, copper 2 hydroxide. This is the driving force. This is precipitate plus sodium sulfate. And then to balance it, we'll need 2 sodium hydroxide. And so this is our stoichiometry here. So we're going to have 30.0 milliliters of copper 2 sulfate. So 30.0 milliliters of CuSO4 solution. And then from there, we're going to convert that to liters, which would be 0.030 liters. And from there, we're going to go to moles using the molarity. So if we know how many liters of copper 2 sulfate solution we have, then we can figure out how many moles if we have the molarity. And the molarity is 0.635 moles of pure copper 2 sulfate per liter of copper 2 sulfate solution. And then we'll do a mole-to-mole conversion here. And then we're going to go to volume. We know the molarity of the sodium hydroxide. And so for every liter of sodium hydroxide solution, we're going to have 0.842 moles of pure sodium hydroxide. And so we're going to flip over the molarity. So we'll go from moles to liters, and then from liters to milliliters. Here. That should take us. So the first thing is to get the equation down. It's copper 2 sulfate plus 2 sodium hydroxide. This is copper 2 hydroxide plus sodium sulfate. Then we're going to go from milliliters to liters, and then liters to moles, and then moles to moles, and then moles to liters, and then liters. They compressed it though. They call the molarity 0.635 moles per 1,000 milliliters. I just do moles per liter. I don't like too many variations. But you could do it either way. We have 45.2 milliliters of sodium hydroxide solution. Now, one thing is I would write solution here because this could be confused with pure sodium hydroxide. And it's not 45.2 milliliters of pure sodium hydroxide. It's 45.2 milliliters of sodium hydroxide solution. Okay, that's some example of stoichiometry. Another example of stoichiometry is using titration. With titrations, we have diurets, we have indicators. We use the indicator phenolphthalein. Phenolphthalein turns pink with hydroxide. This is a phenolphthalein. This is a Chem 1A style titration. This is a Chem 1A style titration because if you add too much sodium hydroxide here, and you overshoot it, you can't go back. You can't go back and forth. If you overshoot it too much, you're going to have to just start over again. So there's a lot of splatter here. They should wash the splatter and mix it. In case that splatter contains acid that needs to be neutralized. From experiment 10, we did standardization. What was standardization again? Standardization was the determination of the concentration to a high degree, accuracy and precision. We typically use primary standards to calibrate things. We're just standardized things. So let's take a look at this titration problem. A 25.0 milliliter sample of an electroplating solution is analyzed for its sulfuric acid concentration. It takes 46.8 milliliters of 0.661 molar sodium hydroxide to neutralize the sample. Find the molarity of the acid. And so in this case, the H2SO4 is being titrated with sodium hydroxide. What forms here? Yeah, water and sulfuric acid. Or no, we have sulfuric acid. Water and sodium sulfate. Okay, I need to balance this. How many sodium hydroxide? Well, here, I need 2 sodiums. I need 2 here. How many waters? In other words, this is double replacement. A is H plus, B is sulfate. AB plus C is sodium ion. AB plus C, D is hydroxide. Swap it. And so the water forms with H plus and hydroxide. Each water is an H and an OH. So one way of thinking about water is it's hydrogen hydroxide, HOH. And so how many hydrogens did I have here? Yeah, and so that means I need to form 2 waters. That means I have 2 hydroxides here, I'm going to have 2 hydroxides there. So it's 2 waters. And now it's balanced. It takes 46.8 milliliters of 0.661 molar sodium hydroxide. And so over here we're going to go 46.8 milliliters of sodium hydroxide solution. And so we'll go from milliliters to liters. Actually, the liters is pretty straightforward. It's just move the decimal 3. So 0.0468 liters of sodium hydroxide solution. And then we know the molarity. The molarity will take us straight to mole. The molarity is 0.661 moles of sodium hydroxide, pure sodium hydroxide, per liter of sodium hydroxide solution. And so liters cancel out, that gives us moles. Moles of sodium hydroxide, then we're going to go to moles of H2SO4. Now, what they want is, they want the molarity of the acid. So if you want the molarity of the acid, the molarity of H2SO4 is equal to the moles of H2SO4, which is this, divided by the liters of H2SO4 solution. The liters of H2SO4 solution is the 25.0 milliliters. We have 25.0 milliliters of electroplating solution. The electroplating solution is the same as the acid solution. So we'll go from 25.0 milliliters, and then that gives us 0.0250 liters, and then that gives us the number here we're going to plug in. So they calculate the moles. The moles come out to 0.0155 moles of H2SO4. That goes on the top using some stoichiometry here. And then if we want the molarity, we've got to divide by the liters. So they convert 25 milliliters into liters at the bottom. And then calculate it. It comes out to 0.620 molar H2SO4. So they get 0.620 molar H2SO4. So that's a titration, example of a titration. There we have titration using normality. Skip this, skip this, skip this, skip this, skip this, skip this. And then we come up to colligative properties. Colligative properties, we're just going to look at 2 colligative properties. The 2 colligative properties we're going to look at are freezing point and boiling points of solution. So what temperature does water freeze at? 0 degrees C. At what temperature does salt water freeze at? Does salt water freeze at the same temperature, 0 degrees C? a lower temperature or a higher temperature? What does it freeze? Salt water actually freezes at a lower temperature.
0 degrees Fahrenheit.
That salt water freezes?
Yeah.
Yeah, a certain concentration of salt water freezes at 0 degrees
Ocean
Fahrenheit.
salt water.
Yeah, it's like some kind of brine. I forgot. Because the ocean, there's different concentrations depending on what ocean you're looking at and what part of the ocean you're looking at. Well, the Mediterranean is very high. Salt. But the brine solution that Fahrenheit used was something I think he made. I think it was a saturated solution of something. And it turned out that was 0. Well, having a lower freezing point is called freezing point depression. So colligative property is freezing point depression. That is, salt solutions freeze at lower temperatures. How about boiling? Do salt solutions boil at the same temperature, 100 degrees? A higher temperature, over 100, or lower temperature, under 100? It turns out it's actually a higher temperature than 100. And that's called boiling point elevation. And so what you should know is that freezing point depression, salt solutions freeze at lower temperature, and boiling point elevation, salt solutions boil at a higher temperature than water. Now, how much higher, how much lower, it's not even. And it depends on this factor K. We're not actually going to do the calculation. The calculation we could do using molalities, and it's a very simple calculation. But K is going to tell us. So for example, for every 1 molal salt solution, the freezing point drops by 1.86 degrees C. It drops by 1.86 degrees, so let's call it 2 degrees C, roughly. So if you have 1 molal salt solution, the freezing point's minus 2 degrees C. 2 molal salt solution, it's minus 4. 3 molal salt solution, it's minus 6. And so depending on the concentration, the more concentrated it is, the more it drops. Now it's about a 2 degrees C temperature drop for every molal. But for boiling, it's only a ½ degree temperature increase. So 1 molal salt solution boils at 100.5, 2 molal boils at 101, 3 molal boils at 101.5. And so, roughly. So those are some of the basic calculations. We usually have to calculate the molality and other stuff. We'll look at some problems tomorrow from this chapter. We'll stop now.